Hello, everybody, and welcome back to video number 41 in this set. I was preparing lecture notes for a summer camp. Got high schoolers coming to the college I work at, where I normally teach game development. It's one of the things I normally teach every spring and fall semester. And there's a week-long summer camp with high schoolers, and I needed to abbreviate a semester's worth of material, actually 2 semesters, the intro and the advanced class, as much as I could get from that abbreviated down to a week instead of 2 semesters. So I wanted to give that lecture a trial run, and part of that was making some videos and editing my notes, and decided to share the videos instead of deleting them afterwards. So that's what these are. It's not the final draft on anything, so there might be little parts skipped over, some edits that need to happen. So it's not the final draft, but I thought, well, maybe it'll be useful for some other people if they stumble across it on YouTube and kind of give an introduction to game development and see a bit of my approach, or just have the full picture there so I can send some of my students this way. Um, so we're up to video 41, getting very near the end. In the previous video, we got our alien moving around after we tested the interaction between character and alien, got it moving around. So we just need to bring in more aliens, and then we'll bring in a boss fight, and that will pretty much wrap up the game. The rough draft of the game, that was one of my tips, is get a rough draft, one that's full of little bugs and errors and doesn't have the final graphics and still needs a lot of polishing done, but is a complete game. Has the cutscenes, so it tells the story of what's going on, and the basic interactions there, and the rough draft of an entire game finished as quickly as possible, and then come back and polish it up. Over the years, I've found that that works much better than trying to polish the steps along the way, and with just a rough idea of what the future of the game is going to be. You actually know what you're polishing up that way. So we're ready for that, but I wanted to do one more content video here, just a brief one. So we talked about just a moment ago the interaction between the character and the alien, which they're interacting with the ground, and that's where the physics comes in. All of our major game engines will have a physics engine, and the thing we actually need from the physics engine isn't the laws of physics. That's probably what people think about at first, but the laws of physics apply where things interact. That boundary around our objects. That's what we have to have from a physics engine. And oftentimes the laws of physics kind of come in with that. And some people, especially starting out, might think, well, there's a physics engine there. It can handle the physics. And that's true. But in this case, it could handle the physics for the landscape, but not our other stuff. And really, in the current state, it couldn't even handle the physics for that. So the landscape was set up as a rigid body. So if you use all rigid bodies, then the physics engine could handle the laws of physics, if you do remember to set up the parameters for it, right? Um, right now, this says this big world here has a mass of 1 kilogram. So the laws of physics the physics engine will not be calculating that correctly. So if you use all rigid bodies and set up all the parameters properly, like the proper measurements for your model, then the physics engine will handle the laws of physics for you. Our player and alien were kinematic bodies, so they just get a little piece of physics, and we still have to handle most of that. So we want to keep that in mind, and we're not doing the calculations, just like in other things. The computer is a machine that does the calculations for us. We just need to set up the equations for it and expressions and put them in the right spot, and maybe do a little bit of that when debugging. But the computer's going to do the calculations, so we just need to make sure we know which calculations to set up and how we want to approach it so that the physics are applying correctly. If you want the physics engine to handle it, you need to use all rigid bodies and be as precise as you can with all the parameters, and maybe create a script that adds a few more parameters that your physics engine can work with. In general, there's only a couple we know that we need, though. So let's take a quick look at the ones we'll actually need. Okay, so the next thing we want to talk about is physics. Um, Not in depth here, just some basic points about what we want to think of, and a few things. So first off, we're going to have computers doing the calculations, so we're on discrete state machines, so we don't need to worry about the infinitesimal change like you would see uh, in a calculus class introducing physics. But we want to kind of inherit some of the terminology from there. So I'm going to use x to represent position, and I'll draw it as a vector. So the little arrow on top is uh, uh, the little arrow on top represent means it's a vector, and really we want to think about that as a function of time. So at some point in time, where are we located at? Hopefully that makes sense, and you can see how that's going to relate directly uh, to the game engine, because the time's going to be the what frame at each frame of the game. Where is our position located at? And that's a vector. That is a vector. I used x, but there's a whole x, y, z thing here going on, right? What's our x position? What's our y position? And what's our z position? So we have all of that information representing our position, but it's going to change. Uh, and well, we're on computers, discrete state machines, so we don't need the infinitesimal change. So I'm going to use uh, a Greek letter delta that represents change. So a change in our position, that's going to be velocity. Velocity is a change in position. Hopefully, no fancy term uh, that's almost used in English, so no new terminology there. And as a vector, when we break that down and think about x, y, and z, that's kind of saying how is our x changing? How is our y changing? And how is our z changing? And delta means change. So the formula for that is end minus beginning. I'm going to run out of space here. Yep, definitely going to run out of space since I put an extra G in that word. Let me see if I can spell that correctly. Beginning. So we take the ending value minus the beginning value, and that tells us how much we changed. And the negative sign gives direction. So that's the thing about vector is it's not just the number, the direction is included as well. Remember thinking about arrows. So if we're like on a 2D plane, the XY coordinates, the arrow going up and to the right is positive, but an arrow going in over in this direction would be negative. So the positive and negative signs give us information about which direction we're going. So that's important with vectors. And I guess we'll take this one step further. A change in velocity, which is a change in the change in position. So the rate at which our velocity is changing, that's going to be acceleration. So change in the x velocity, change in the y velocity, and a change in the z velocity. So all of our vector components are still separate, but really as our velocity changes, that's acceleration. And that's going to be one of our most important values as we talk about physics here. But this path would continue. If you've had a calculus class or maybe a physics class, you've heard some of the other ones. So a change in acceleration is a jerk, and a change in a jerk is a jump, and a change in a jump is a nudge. And we have words for them going all the way down, which make nice variable names when you're setting this up. Um, and these are all functions of time. I dropped the function notation pretty quick here, but it's a position as a function of time, then velocity as a function of time, and acceleration as a function of time. and so on. Jerk is a function of time, and jump is a function of time, and nudge is a function of time. And so it's a function. Um, one output for a given input, which means a computer can calculate all these things for us, and we just need to set up the equations. And in particular, we want to think about Newtonian physics. Really, just a couple of points of Newtonian physics. For development games, we really just need two of Newton's laws. Um, Computers are discrete state machines, so obviously analytical mechanics would work a little bit better. Um, the people who see that as in undergrad studies, it's going to be a 400 level course, analytical mechanics, where we define a state and then define an action on that state. And hopefully that the terminology I just used kind of reminded you of a game engine, what we're doing in a game engine. And thing about that in physics is it always ends up in Newtonian equations if we defined it correctly anyway, is sort of a check. If we don't get back to Newtonian physics, then that means we defined our action incorrectly. So that would be better if you've seen that, but I'm just going to jump up to the parts of Newtonian physics we would need for game development. I'll make a new page to do that. And I don't want these videos to get super long, so I'm just going to go ahead and jot down the two things we want to think about. Force equals mass times acceleration and inertia, which is really conservation of momentum. So force equals mass times acceleration. Things move because forces are applied, right? Everything moves because we're pushing in some direction or another, pushing or pulling in some direction. And we get that push or pull by taking the value of the mass times the acceleration. And mass is a constant. So the only thing we can really control here is the acceleration. We adjust our acceleration in the code. Mass is a constant, and the result of that is a force that moves our object, which should seem an awful lot like in the real world. It's how things work in the real world. We control, say, a car. We control a car by the acceleration. The gas pedal being the positive acceleration and the brake pedal being the negative acceleration. The mass of the car doesn't change, but then that gives us a force which moves the car. So the acceleration is what we have control over. And just like our car, that's what we want to control in our game engine. And acceleration is changing velocity. So to get the best movement in your characters and other things in your game, you want to make sure you're thinking of it just like your car. You're controlling the acceleration. So the gas pedal is positive acceleration, the brake's negative acceleration, but that's what you have control over, and then it builds up to the forces applied on the car. Another little change on that is going to be impulse. We probably want to think about impulse. I'm going to write that as delta P. Impulse is change in momentum. We'll get to momentum here in just a second. Oh, and there are a whole bunch of vectors here. Force is a vector. It applies in a direction. Acceleration is a vector. So this is the change in our force over a time interval. A standard example of impulse is like if we have a car and we're moving along and we want to bring that car to a stop. There's two ways we could do it. We could hit a brick wall, right? Hit a brick wall, it's going to stop immediately. Or we could hit a row of bushes. And obviously, if this car is moving, it's going to take the same amount of force to stop it. But there's a big difference between hitting a brick wall and coming to a stop and hitting a row of bushes and coming to a stop. The brick wall is going to destroy the car, and the bushes are probably going to scratch the paint a little. And the difference there is the time interval over which that force applies. So you probably won't do a lot of coding directly for that, But that's something you want to keep in mind. It's not just what force is being applied, but over what time interval is that force being applied? So how much effect does it have? And the other one we'll really need for game development is inertia, which whoops, let me try to make sure that pen doesn't get in the way of the video. So I'll turn it on over here and then move it over. So inertia is really conservation of momentum. Which I'm going to use a P with the little vector arrow on top of it. So if we have, we have some, we want to set up momentum. So we have some mass, which is a constant. So we can't really change our mass. I'm going to put a 1 beside it. So we have mass 1 moving at some velocity. I'm going to drop off the arrow hat. Well, I'll go ahead and draw it. It's quick to draw an arrow. So this mass is moving at some velocity. Maybe that's our character running through the world. And we have another mass. I'll put little 2's here. Another mass moving at some velocity. Maybe that's some stationary prop, like a chair sitting in our game world. So its velocity is 0. When we add those up, we don't lose anything. So that's equal to whatever that mass is moving afterwards, although its velocity will probably change. Right? If we run into a chair, our character is going to slow down, but the chair is going to speed up. Its mass won't change, but its velocity will. For an example, our character is running along at full speed, a big, heavy, human massive character moving at its top speed runs into a chair that's standing still. And afterwards, the character is going to slow down a little and the chair is going to speed up a little. But if we added all those velocities and masses back together, we would have the same amount. There's also an energy factor in the real world, like sound and heat and things that. So some of that energy goes there. But for game development, we can just worry about these pieces. It's going to pass and not get into the energy too much, but that would just be plus the energy at the end. Well, I might as well write it. Plus any energy we get. So the sound that goes off, the heat from friction in the impact, and things like that. But everything is conserved. So you don't want your character running along at full speed, run into a chair, which if you didn't adjust your masses, they'd have equal mass, and that would bring your character to a stop suddenly. That's not what would happen if we would do that. So those are the 2 laws of physics we need to think about the most. Both of 2 of Newton's 3 laws. So force is mass times acceleration, and often at least keep in the back of your mind that that is going to apply over time. It's not an instantaneous thing. So in general, try to avoid doing that in one frame of your game. And conservation of momentum, which is inertia, which means that when we have a bunch of things, the masses moving at different velocities and they collide and interact with each other, we should not gain or lose anything. The velocities after the collision should balance out with the velocities beforehand. Those are the ones we need, and remember you'll get most of your control by applying forces. Mass is constant, so we have our acceleration, and acceleration is change of velocity. So just like controlling your car, you get most of your control by adjusting the velocity. Same thing in game engines. So I wanted to introduce some of that. And in the next video, we'll finish that up. I just wanted to talk about physics a little bit, but if you're serious about game development, you should probably do an in-depth study of physics somewhere along the way. I'll see you in the next video, and we're almost finished with the game. We just need a bunch of aliens to fight and then a boss scene. And then we'll be finished with the rough draft of the game. I'll see you in the next video.